Hello everyone, welcome back. So let's reach the point where we have points being scattered on the active geometry on one cluster, and now we want to proceed with creating debris emitters. And one thing I wanted to illustrate, when we have an object, when we have a geometry transforming, let's say put down a transform, and I'm going to use $FF. And if we play through it, let's increase this by 2. If we play through the frames, you can see the geometry is moving. And if we, let me use a time shift. So let's say we're at frame 1, and then we're at frame 2. And let me template this. Right now, the geometry is moving from this position into this position. When we pass this, when we convert this into a volume and pass it, it's not going to create gaps, but it will create an emitter that looks like stamped spheres. Okay, and if we lower the speed, let's say 0.2, you can see that the two spheres are overlapping, and this is going to produce a much smoother emission. You know, let me do, it's a very common problem, but let me do an example with points. So let's scatter points on the geometry and let's transform those points. Let's use a pop net and let's dive inside. I'm gonna say I don't need any velocity. I want the points to stick in space. And I'm going to use all points. So if we hit play, you can see we're getting a stamped copy of the spheres. And the only way to fix this is by increasing the substeps. And you can see now we have, it looks like a continuous emitter. But we don't want to do substepping with smoke solvers. And so that's one of the problems we want to solve, and I have a solution for that. And the solution is to take these points, and let's say we have these points belong to a specific piece. Let me increase this to 1 million. So this is one piece, and instead of using those points as an emitter, I'm going to take copies from previous frames. Let's do this. So I'm going to say time shift this F-1. Sorry, this one. So we have this frame and we have the current frame. I'm going to merge the two together. And if we keep adding copies, enough copies, we'll create a volume that is filled with points, and then we're going to convert that into an emitter. But I'll explain once we set this up. Will become much more clear to you guys. But the thing is, what I'm trying to do now is something different. We have these points. We're going to be able. I have a solution where we can use these to emit smoke. To emit debris and smoke without having to increase the substeps. But so that's not a problem. But the problem is we want to be able to stop the emission at certain points, because right now everything is continuously emitting. We don't have any ways of turning the emission off. And the solution that I have is to analyze, or the solution that I want to implement is to analyze how far each piece has traveled and create a mask based on that. So let's say, let's go here. So let's say we have, let's say this is the final frame. Okay, we have debris that reached this point, and we have a debris that reached this point. Some of them went up and came down. Those that went up and came down, we don't want them to continuously emit until they reach a still point. We want them to emit over the first maybe half of their path, of their traveled path. And to do that, we need to find a way what path they went through. We need to analyze that. The pieces that traveled very far off, for example, each debris contains a specific amount of sand and dust and things like that stuck to it, and it's not going to emit all the way until it reaches a final destination. It can emit everything it has in the first 10 frames of its lifetime, or if it's a traveled path, and we need to be able to do that. So what I'm going to do is I'm going to create a system that tracks the position of all the pieces and the path they went through, and we're going to create curves for each of the pieces, and then use the length of that curve, or use the length of that curve to create a mask that we can use as a multiplier. So instead of trying to explain this, I'm going to implement this. So let's go to one of the clusters. This one is fine. And I don't need, let me copy this. I don't need the points, I need the geometry. Okay, and I don't want the actual geometry. I'm gonna assemble this, and we need packed geometry. I'm gonna convert it into centroids because I need 1 point per primitive. Okay, that's all that matters. And then I'm gonna go to the last frame. I'm gonna use a trail node, and with this trail node I'm gonna take the current frame. Let me open a calculator. I'm gonna take the end frame, so all these points, we have 240 frames. Come on, we have 240 frames. The trail increment is the number of the substeps. Think of it as the substeps. So I'm gonna divide that by 8. 8 substeps is going to be enough to give me enough substeps. And the trail length, by dividing the total frames by the trail increment, we get the trail length. So I'm gonna set this to 30 and this to 8, and then I'm gonna copy this. And what this is going to do is it's gonna traverse back every frame and give us a copy of the geometry at that frame, and it's gonna go all the way. The total number of frames that it's gonna travel is 30 multiplied by 8, and so we went all the way back to the first frame. Okay, so I generally set this to something high, 4 to 10, and then divide the frames by that number, and that gives me the trail length. And if we look here, this is the end position. If we go back, see, for example, this point here, this primitive, this piece, you can see the points there. That's its travel path. And now what I want to do is I want to connect these. So let's put down the time shift. We need to do this at the last frame. So delete time shift. And we want to connect all these points. Now, to create primitives out of points, we want to use an attribute. Well, what that attribute is in this case is the name attribute. That's what we want to use. If we go under polygons, I'm gonna add an add node, go under polygons, and then by group, I'm gonna change this to by attribute, set it to name. If we look at this now, we have a path that each piece has traveled. And what this will allow us to do is we can do multiple things. We can, for example, measure the length of each primitive and then create a mask based on that. So if sorry, not a mask, but let's say the length of this curve is 5 and the length of this curve is 1. We can use this information to reduce the amount of smoke being emitted over time, because this one has traveled much less, so it has emitted much bigger volume over its lifetime versus this one. This one is moving really fast, so the emission is weaker over its lifetime. And it's this long piece, it's not going to emit forever. It's going to probably emit from 0 to here and then stop. So all of this we don't need. And what I'm going to do is I'm going to use a UV texture to get a gradient over these curves. And I'm going to set this to arc length, and I need a point attribute. And let's create a wrangle node. I'm going to create a float that represents this gradient. So I'm going to call this curve u, and it's equal v at uv.x. It's the x coordinate of the UV that was just created by this node. So if we create a ramp now from that curve u, we get this nice gradient, which is very, very cool. And we can do this. We can say, okay, debris emitter, don't do any more emission after this point. Okay, and this is also a good way to see how far the pieces have traveled, and probably we should add a delete node to delete anything that went past this region, and we'll do that. I'll do that in the next video. We will truncate the points so it only we only work on a region. We don't have to worry about all of this. So with this mask, it's going to help us see, for example, this one, it went up, and then as it starts going down, it's going to stop emitting. We can analyze this. But to copy this information back onto the geometry is actually a tricky problem, because at this point we have just one curve and it's static. So how do we get, where are they? How do we get these points to do a lookup on the curves? So here they don't know anything, these points, they don't know anything about the emission, about the path, but we want to sample them. Well, we can, we have a way to do primitive lookups using a value that goes between 0 and 1, which is the UV coordinate basically of a primitive. And that function is called primuv. But for it to work, we need to know which primitive this belongs to. Okay, which piece this primitive belongs to. And we somewhat know this. We have a name attribute. So we know the name attribute on this. We know the name attribute on this. And it's the same. So what we can do is we can create a primitive attribute and then copy that onto the geometry. So let's do that. Let's create a wrangle node. I'm going to call this, it's an integer. I'm going to call it PR, and it's equal to prim_num. Okay, so that we have a PR, and then I'm going to use a copy attribute, an attribute copy, and I'm going to copy this PR onto the geometry. I don't have to do it every frame, so I can just do it here and then transform. And I'm going to copy, I'm going to match by the name attribute, and I want to copy the PR attribute. Okay, let's do a test. Let's say, let's blast. Let's do a quick lookup. So let's say, what's the, so this PR, for example, at PR equal this number. I'm going to delete non-selected points, and now we have a piece. Okay, so that's the geometry there, and I'm going to copy the same one. I'm going to do it here. I'm going to do it on the primitive to verify that I have a connection. So let's template this, and this guy should start in here, and I think it does. It's just because we are in the transfer mode. So if I check this, yeah, it should match, because the position of the pieces shifted once we do the RBD. And so if we look at the first frame after we transform the points, it's perfectly there. And if we play through, this, it should transform. Okay, so that one is transforming here. Yep, so that's the piece. If we play through this, it's going to travel exactly on top of that path. And what we want to do as it travels, we want to sample the curve, the curve color, which is black to white, white to black, and we want to use that information as a multiplier. So let's create a point vol. I'm going to dive inside. I'm going to connect the second input here, and let's do all the primitives. I don't need just one. And let's dive inside. What we need to do is we need to use a primitive, let me remember the name. Yeah, primitive attribute. And what it's asking for is asking for the geometry that we want to do the lookup for, and that's going to be the up input too, because we're connecting. We want to do the lookups from these primitives. Now the prim attribute is that PR attribute that we copied. So that's an integer. It's a PR. Let's connect that, and let's plug this into the color. And what I want to sample is I want to sample this curve or let's sample the color attribute, which is CD. So here it's by default it's sampling that. Okay, and if I change this U attribute, right now it's 0, which is here. So if I change this, see how it's changing from from black to white. And what we need to do is we need to generate this U attribute, and what I'm going to use is I'm going to use the frame, the current frame. So as this goes, I'm going to use the frame number to create a normalized value that goes between 0 and 1. And the easiest way to do that is by taking the current frame and dividing that by the total number of frames. So let me promote this. We have a total of 240 frames, and if I connect this into the color, you will see as I play through, it's going to start black, which is equal to 0, and as we go through, you will see that it's going to change to white. So that's our normalized value. I'm going to connect that into the U coordinate, and then we're going to use that to do the lookup. So if we play through now, it should give us the color information from the primitive. And let me check. Let's see. So let me delete this blast. I want to do it on all the geometry. Yep, see it's working. And we need to invert this, so the end, no, it's correct. So everything starts white and it starts emitting. We still have to add another thing, but as we play through this, you will see that pieces are transforming from white to black. No, we need to invert this. Sorry. Yeah, we need to negate this. So I'm going to use the complement. And everything should start, everything should start white. And then as we play through, it's going to fade into black. Yeah, this is it. This is working now. And so that's the emitter that we can use as a multiplier to control the emission. And everything is controlled through this curve, so we can turn them off sooner, we can keep them on for longer if we wanted to. You can see now they're staying white for a much longer period of time. And so that's what I call normalized emission, and it's based off the path that each piece has traveled. It's not necessary to have this, but it's a nice way to control if you want to further control over the emission and when a geometry is considered as an emitter or not. And look at this part, for example. This is a very tricky thing to do. We're only going to consider pieces that are going up, and then as they go down, the emission is fading off nicely here, which is a very hard thing to do with an automated system. So this is one of the ways to separate or multiply the emission of the geometry, and we still have something else that we want to add in the next video. Thank you guys for watching.